Hey there. In this video, we're going to learn how to find the determinant of a matrix. A determinant is a scalar value that is computed from the elements of a square matrix, and it provides us information about the matrix. So when I'm finding the determinant, I'm getting a number out of my matrix. And for notation, if I'm talking about a generic matrix, say A, then I will put a DET in front of it. If I'm actually rewriting the matrix and finding the determinant, instead of putting brackets around the matrix, I will put just vertical lines, so almost like an absolute value there instead of a bracket. So make sure you're differentiating between those two when you're talking about determinants. Now, some things to know about a determinant. We're only defining them for square matrices, so you're not going to see like a 2 by 3 or a 4 by 2 or anything like that. It'll be a square matrix each time. The determinant will tell me something about the inverse of the matrix. It turns out a matrix A is invertible or non-singular, so it has an inverse, if and only if the determinant of that matrix is not 0. So if I take the determinant and I get something other than 0, I know that it's invertible. And if I know it's invertible, I know that the determinant will not be 0. If the determinant is 0, then we call that matrix singular or sometimes non-invertible, which just means that it doesn't have an inverse matrix. And we have used matrices to solve systems of linear equations. So it turns out that if you get a determinant other than 0 for the coefficient matrix, then the system has a unique solution. If you get 0 for the determinant of the coefficient matrix, then it either has infinitely many solutions or no solutions at all. Okay, so let's learn how to find the determinant of a matrix. And we're going to do this based on the size, starting with a 2 by 2 matrix. This is my first square matrix that I can find a determinant for. And I'm going to do that by multiplying along the diagonals. So the main diagonal in this matrix, I have elements A, B in the first row and C, D in the second row. So to find the determinant, I will multiply down the main diagonal, A times D, and then subtract from that the product of the other two numbers going in the other direction. So A times D minus B times C will give me the determinant. And another nice thing that we get from the determinant of a 2 by 2 matrix is a quick way to find the inverse of the matrix. As long as the determinant is not equal to 0, which means it's invertible, then I can find its inverse by taking 1 over that determinant and multiplying it by this new matrix where I've taken the original and swapped the values in the main diagonal. So A and D here would switch positions. And then the other two values change sign. So they stay in the same position, but they become negatives. So let's do an example where we find the inverse of a 2 by 2 matrix using this formula. So I got my formula here. I have a matrix A, which has rows 6, 9, and 1, 3. So first thing I'm going to do is find the the determinant of the matrix. So I'm going to rewrite my matrix using the bars instead of the brackets. And then I'm going to multiply the main diagonal, so 6 times 3, minus the product of the other two values, so minus 9 times 1. And so that's going to give me 18 minus 9. I get a determinant of 9. Using my formula for the inverse, I'm going to take 1 over that 9 and multiply it by this new matrix. So the new matrix is going to have the main diagonal switched. So the 3 and the 6 have switched positions. And the 9 and the 1 become negative. And I get the determinant. I just take 1/9 times that matrix for the inverse. And I could leave it in this form, or if you wanted to multiply that 1/9 in, this is just scalar multiplication. So I just multiply each of the values inside the matrix by 1/9 and simplify to get the inverse. Okay, let's do one more thing with a 2 by 2 matrix before we move on. I can use a rule called Cramer's rule to solve a system of two linear equations using the determinant. Okay, so what we're going to do here, I've got this system a11x plus a12y equals b1, and then a21x plus a22y equals b2. And I can pull out the coefficient matrix, so just taking all those a's. And if I take the determinant of that coefficient matrix, we're going to call that determinant just D. And then I'm going to create two other matrices and find their determinants. So the second one, we're going to call it dx. And I've taken the coefficient matrix and replaced the x coefficients with the b1 and b2 on the other side of the system. And I find that determinant. And dx divided by d will give me the x in my solution to the system. And then for dy, this time I take the coefficient matrix and I replace the y coefficients with b1 and b2 and find that determinant. And then y will be equal to dy over d. Okay, so just by finding three determinants of three 2x2 matrices and then dividing the values, I get my solution very quickly. So it's kind of a cool thing. And Cramer's rule does apply to larger systems, but the computations become so inefficient that we typically don't use these for larger models. We don't use this rule for larger matrices. So let's do an example with this one before we move on to finding determinants of larger matrices. So use Cramer's rule here to find the solution to the system 2x plus 3y equals 5 and 4x plus y equals 6. So first thing is I'm going to bring back my formulas. So here's all the matrices I need to set up and find the determinants for, and then how I will use those to find x and y. And so first I'll find the matrix D. So that's just the coefficient matrix. So 2 and 3 from the coefficients of the first equation, and 4, 1 from the coefficients from the second equation. And then I'll find the determinant. So 2 times 1 down the main diagonal minus 3 times 4, and plug that into a calculator, and I get negative 10 for that determinant. So for my calculations for x and y, this is going to be the denominator. Now I'm going to find the numerators for each one. So for dx, I'm going to take this same matrix that I just found a determinant for. I'm going to take out the first row and replace it with the 5 and the 6 from the other side of the equations. And then find the determinant again. So 5 times 1 minus 3 times 6. And plug that into a calculator. I get negative 13. Okay, now I am ready to find x, but I'm going to go ahead and do the last matrix before I plug everything in to find x and y. So dy is going to be the coefficient matrix again, starting from the original, and now replacing the second column with the 5 and the 6 and finding the determinant. So 2 times 6 this time minus 5 times 4 will give me negative 8 for dy. Okay, so to find x, I take the determinant for dx, which is the negative 13, and divide it by the negative 10. And I'm going to go ahead and simplify this to a decimal, so I get 1.3 for that first one. And for x, I just switch out the negative 13 for negative 8. And so negative 8 divided by negative 10 will give me a y of 0.8. And now I've got the solution to this system without having to do any algebra, just a little bit of determinants. Okay, so now if we add another dimension to our determinant, going to a 3x3 matrix, let's see, how do I find the determinant? Now, there is a method we'll look at in a minute called cofactor expansion, but there is a trick for 3x3s that I'm going to show you first, so this can save you a little bit of hassle. Cofactor expansion is a little bit more work. So how this is going to work is I'm going to take my 3x3 matrix, and I'm going to take and the first two columns of the matrix, I'm going to replicate them on the outside of the matrix to the right. So I'm going to rewrite my matrix with the first two columns rewritten off to the right. And what this allows me to do is it expanded out my matrix, and it gives me more diagonals, kind of like what we were doing with the 2x2. In fact, it gives me 3 diagonals going down to the right. And so what I do to find the determinant is I will multiply the 3 numbers in each diagonal and add them up. Okay, so I get the main diagonal of the matrix, and then by extending the matrix out, I get 2 more diagonals that I can multiply there. So I'm going to get 3 numbers from those 3 products. And then I go to the diagonals going down to the left. So I get 3 more diagonals going in the other direction. And I do the same thing. I'm going to multiply all 3 numbers in each diagonal and add them up, and then subtract that from the first diagonals that I found. So it's a lot of notation there at the bottom. It's a little easier to see this in action with an actual example, so we'll do that in a second. Okay, so here I have a 3x3 matrix. I've got, and it's just the numbers 1 through 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9 are my 3 rows. And I've duplicated those first 2 columns on the right side of the matrix. So I've got those 2 columns there, and that's going to give me a few, or all 3 of my diagonals in each direction. So to find this determinant, I'll start with those 3 diagonals going down to the right. So I end up with 1 times 5 times 9, 2 times 6 times 7, and 3 times 4 times 8. And those products are all going to get added together. That's the first half of my determinant. Okay, and then the 3 diagonals going down to the left, I will find those 3 products, and I'm going to subtract the sum of those from the first ones that I already have here. So I've got 7 times 5 times 3, 8 times 6 times 1, and 9 times 4 times 2, all multiplying. And I should have some brackets around that. I missed it. Those last 3 products should be added together and then subtracted from the first 3 products. So I ended up with the first 3, my diagonals going down to the right. I got a total of 225. And I also got the same thing going down to the left. So 225 minus 225 gave me a determinant of 0 here, which means that this is a singular matrix, does not have an inverse. Okay, so there's your trick for a 3x3. You can use cofactor expansion though as well. Typically, I hold off on this until I get to a 4x4 or bigger. So a cofactor expansion is a method of expressing the determinant in terms of smaller determinants. We call those smaller determinants minors, and then they have these corresponding cofactors that we will use to find the determinant. So if I have this n by n matrix A, I'm going to get a matrix that's just 1 row and 1 column smaller, called the submatrix. So it's a matrix within the bigger matrix. We're going to call that M, and specifically Mij, depending on how I got the matrix. And we obtain it by removing the ith row and the jth column from the matrix A. So, for example, if I wanted to cross out the first row and the first column, that would be the submatrix I would get would be M11. The determinant of that matrix is the minor. And if I take that determinant and multiply it by -1 to the I plus j, I get the cofactor. So as an example, let's cross out that first row and first column of this matrix. And so M11 is all the matrix that's left over. Right? And for some of these cofactors, you're going to be crossing out the ones in the middle, and so you just take everything except for those. You just remove that row and column and squish everything together to get another square matrix. Okay, so the minor for A11 would be the determinant of this smaller submatrix. And then to find the cofactor, I would multiply that by -1 to the 1 plus 1. Or here, that would be -1 squared, which is just 1. So the signs are going to alternate as you do this. Okay, and so once I've found the cofactor for that term, I multiply it by the number that was crossed out twice, the one in that row and that column. So for this example, it would be A11. Okay, and so we do this for a whole row. Typically, I just go with the first row, but you technically could pick any row in the matrix, and you cross out that row, cross out a column, find the cofactor, and then move to the next column, cross out the first row again, cross out the second column, find the cofactor for that matrix, and you go all the way to the end of the row. Okay, again, it's a complicated process to describe in general like this, so let's do an example to get this a little more concrete. Okay, so I'm going to stick with a 3x3 just because it becomes much more work the bigger the matrix is, and we're going to use cofactor expansion on it. Okay, so the determinant here, I've got 8, 4, 1 in the first row, 5, -5, 0 in the second row, and 2, -6, 7 in the third row. So what I do is, for the first one, I'm going to work only with the top row. So I'm going to cross out the first row and cross out the first column. And so I get the submatrix M that is -5, 0, -6, 7. I'm going to find the determinant of that matrix and multiply it by the 8, because that is the one in row 1, column 1, and I crossed out row 1 and column 1. Right? And then I'm going to continue to cross out the first top row, but now switch to the second column. So I'm crossing out the row with the 4 at the top. And so the submatrix I get now is the 5, 2 on the left and the 0, 7 on the right of the row that of the column that I crossed out. And I'm going to multiply that by the 4, the one that's in the position, the row 1, column 2. Okay, I'm almost done with the row. I go to the third column now, cross out the first row, third column. The resulting matrix is everything to the left of that third row. So 5, -5, 2, -6. Okay, and then I multiply it by the 1 that was in the row and column that I crossed out. Okay, now the -1 to the I plus j, that really just makes the sign alternate as we go. And we always start with positive in that first row 1, column 1. So this is going to go plus, minus, plus for the terms. Okay, next up, I need to find the determinants of these 3 matrices that I found. Okay, so for the first one, I've got the 8, and then it's going to be times -5 times 7 minus 0 times -6. I'm just finding the determinant of that 2 by 2 matrix. And then I continue that for the other 2. So then I have -4 times 5 times 7 minus 0 times 2 for the second matrix. And then plus 1 times 5 times -6 minus -5 times 2. And I think I have a negative missing there. That should be a double negative on the 5. So there's a little typo there. Okay, from here, it's just plugging everything into your calculator. I'm going to do a little simplification as we go. That negative on the 5 is probably going to mess my answer up, though, so I'll have to make an adjustment and make a note in the video. But I ended up with -460. So that should probably change after I fix the sign on that one. As you can see, it's really easy to make a little mistake with these. But that is how you do a cofactor expansion.